Hello, good evening. This is Professor Lemire with our latest screen capture video. Tonight's edition, we're doing the conservation of energy, or also called the first law of thermodynamics. I took a little head start here to make sure that we keep this under a reasonable amount of time. And so I wrote a few notes here that should help you out. I don't feel so bad about this because I'd already assigned in homework number 5 for you to read section 5.3 in the Munson book, which goes over this derivation in some detail. You know me, I'm nothing if not humble, but I'm going to argue that my presentation of the derivation is better than that one in the Munson. So here we go. What's the conservation of energy? Well, as I stated too many times in class, you can refer to it as the fact that energy can neither be created nor destroyed. Just like mass, just like what we said for conservation of mass. What that translates to specifically in terms of rate changes of energy now is that the time rate of change of energy in a system in a system, so that means a fixed mass of particles, is equal to the time rate of net heat addition to the system, because heat is a form of energy, of course, plus the time rate of change of, what do you think it's going to be? Work done by the surroundings on the system. Okay, so this is the system representation of conservation of energy. That's what the great philosophers first realized was happening, and that's what we're using up to this point today. It has not been proven wrong yet. Can't create nor destroy energy. So what is energy? Well, energy is, we're going to denote it with the big letter big E, to represent the total energy of a system that has mass m. So if big E is the total energy of the system, that makes it an extensive property. And the corresponding intensive property of that system then is big E divided by m. Okay, so either big E for the extensive property, we're going to call that the stored energy of the system, and little e is also called the stored energy of the system, but per unit mass. So E is the energy per unit mass, stored energy per unit mass. Okay, so what makes up this stored energy? What are all the components of it? Well, we've all seen this before. There's the main components of stored energy are the internal energy, also called the thermal energy of the system. This is why a cup of water at room temperature has less internal energy than has less stored energy than a cup of water that you put in the microwave for a minute. That's because the component of energy stored energy made up of internal energy is higher in the hot water than the cold one. Kinetic energy, that's the energy that's due to the movement of the particles. Half mv square is what we're used to thinking. So therefore the kinetic energy per unit mass is simply v square over 2. And the potential energy, the energy due to the position of the particles above a datum, mgh is what we're used to seeing. So per unit mass is going to be mgh divided by m, or gh, or according to a datum that goes with z, g times z. So therefore the total stored energy is going to be the sum of these three different forms of energy: internal energy again per unit mass, kinetic energy per unit mass, and potential energy per unit mass. So that's it for the stored energy of the system. Now we talked about heat, so let's go over that a little bit more. That's one of the things that can change the total stored energy of the system. So we're going to use the letter Q to denote the heat energy added to the system, or the rate at which that heat energy is added. We're going to call it Q dot. Similarly, the total work energy that is being added to the system, we're going to denote that the letter W, or the rate at which rate is being transferred into the system is W dot, and of course the time rate of change of work is power. Remember from basic physics, work is defined as force times distance. So therefore the rate at which we're going to do work on a system is going to be force times distance over time, or velocity. Force times velocity. We're going to use that in a few minutes to illustrate an important point. But for the time being, let's just worry about Q dot for heat in and W dot for work. Okay? Alright, so how do we go from this system representation to a control volume representation? Well, we're getting pretty good at that. We're using Reynolds transport theorem. Reynolds transport theorem. So let's look at how we would use Reynolds transport theorem to do that. So I've got a system with total energy big E sub cis, okay, which I can get by integrating over the volume of the entire system by multiplying the density at any point within the system times the stored energy per unit mass times dV of that system. Okay, so by this time this should be pretty clear to you why those two guys are the same here. Okay, so we've got that now in a nice form that we're used to using Reynolds transport theorem with, but we're not going to use it just yet. We're going to express the statement of conservation of energy on that quantity on the left here. So we're saying that that's equal to the total energy being added to the system. The rate of change of the stored energy is equal to the total energy added to the system, which is made up of two parts, heat and work. So we've got Q dot net in for the rate of heat addition plus W dot net in for the rate of work addition onto the system. All this is system based. So that's our general statement of conservation of energy. All right. Now we're in good shape to start applying Reynolds transport theorem. And what I'm going to do here is I'm going to use a representative control volume on which I'm going to apply Reynolds transport theorem. And I'm going to use the RTT number 1 form, the restricted form of Reynolds transport theorem, and simply generalize it afterwards to RTT number 2 and the general RTT form afterwards without proof. So we'll prove it for RTT number 1. Okay, so let's look at an appropriate control volume, and I'm going to use some of my witchcraft here to speed things up. Look at that. Okay, bring that puppy back there. Oops, come on. There we go. Okay, it's looking all right. Okay, so that's the system that I want to use for, and control volume that I want to use for Reynolds transport theorem. So we've got flow in a pipe, for example. We've got a fluid of fixed mass quantity that's illustrated in red. So that represents our system at time t equals 0. At time t equals 0, this system, it matches exactly an outline in blue that corresponds to our fixed control volume in the pipe setup. At face number 1 of this pipe, we have a velocity that's coming in at speed v1. At face number 2 in the pipe, we have a velocity that's going out at speed v2. We're adding some heat to the system in this part of the pipe at a rate q dot in, and furthermore, we've got a propeller here shown in green that's adding work to the fluid, so adding energy in the form of work to the fluid, shaft work, with a rate w dot in shaft. I'm going to put shaft here to differentiate it for something else that we're going to do in a few minutes. Okay? All right. So what do we have here? We have one inlet and one outlet, right? Denoted by 1 and 2. We have uniform flow properties at the plane 1 and the plane 2. At inlet and outlet. Remember, I'm not saying that the properties are uniform throughout the entire control volume. I'm just saying that they're uniform along the plane through which there's mass transfer in the control volume. That's all we're saying. And 3, the flow is perpendicular to the inlets and outlets. Use the plural here, but of course we only have one in and one out. Okay, so with these 3 conditions, what's the form of Reynolds transport theorem I can use? That's right, RTT number 1, the restricted form. Okay, so we've got RTT number 1. We know how that works. Let's go with it. It's telling us that the derivative of the integral over the system of rho e dv must be equal to the derivative of the integral over the control volume of rho e dv. Okay, and that's our unsteady term. Minus rho v a times little e at the inlet plus rho v a times little e at the outlet. That's our Reynolds transport theorem. And of course, because of conservation of energy, as we stated before, this guy right here on the left is equal to Q dot in net plus Q dot, plus work dot in net. I say net because there could be some work being extracted from the system and some work being added to the system. And really what I care about is the balance of those two things, the net inlet of work, the net addition of work to the system. At a time t equals 0, the system coincides with the control volume. So while strictly speaking, this energy addition was for the system at t equals 0, which is where I'm applying Reynolds transport theorem, this is the heat and the work done on the control volume. Okay, so our statement of conservation of energy was this, but Reynolds transport theorem allowed us to say that. So therefore, the net result for Reynolds transport theorem is, oops, I'm supposed to see that, this guy right here, first form of Reynolds transport theorem. Bit, bring that over there. Oops. There we go. Reynolds transport theorem, first form. Et voila. Okay, but we're not quite done yet. Not quite done yet. We've got a little bit more to do. You should recognize here, there's one more thing here that I didn't, a step that I skipped. This guy right there is, of course, equal to m dot in. This guy right there is m dot out. Hence, how we ended up with these form right there. Okay? All right. Moving on. I want to highlight a special feature of the work input to the system. Okay, the work input to the system can really be broken down into two parts. The first part is the shaft work that would correspond to the propeller in the little control volume I showed you before, plus another type of work that I'm going to call flow work. Okay, flow work. What is this flow work? Well, it comes from the fact that the rate at which we do work is equal to the velocity, the force vector dotted with the velocity vector on a fluid. You notice here that the rate of doing work to the control volume is a scalar, but each of those guys on the right hand side is a vector, right? Of course, the fact that we've got a dot product in between turns this vector into a scalar. So what this tells us is what we're really interested in is the orientation of the force acting on the control volume and the speed or the velocity at which the fluid flows into the control volume. So that would represent a form of work, the flow work. Okay, so what are the forces that create this kind of flow work on our control volume? Well, it would be the normal stress that's acting on each of the surfaces of our control volume. So let's look at what they look like. Normal stress correspond to forces acting on the control volume surfaces. So in our case, what we're looking at is our control volume. I'm not showing the wall of the pipe, I'm just showing the control volume, which has these two sections, 1 and 2. And the velocity that comes in on that side and the velocity that goes out on that side. We still have a normal, okay, these are vectors, so we put those down. We have normal vectors at each of the surfaces, and these normal stresses acting on the surfaces are due to the pressure of the fluid. So we've got a pressure force. Remember, pressure is a scalar, but the pressure is acting inwards on all of the surfaces. So I'm going to have a pressure force on each one of these surfaces. And since it's a scalar, I have to multiply it by the normal to get the vector force that acts in that direction. So in this case, I'm going to have the pressure times the area, a scalar, times minus the normal vector in order to get the vector pointing in the right direction over here. Similarly, on that side, I'm going to have the pressure times the area, a scalar, times minus the normal vector to that area to get the proper direction. At the top and bottom, what we've got is the same thing. I've got PA times minus N, PA times minus N. Okay, but we notice that these forces, these vector forces, are exactly orthogonal to the velocity that I have anywhere in my control volume, so therefore this dot product over here is going to be 0 everywhere along the perimeter. So the only place that I care about is where there's actually flow into the control volume, hence the name flow work. Okay, so let's break this down into the two surfaces. The inlet surface at 1 and the outlet surface at 2. Okay, I'm going to refer to something. I'm going to use a subscript 1 for in and 2 for out. So at 1, my work in due to flow work is going to be equal to the force times the velocity at 1, which is equal to P1 times A1 times N, times minus N dotted with V at 1. Okay, so this is equal to minus P1A1, just a scalar, times N dotted with V at 1. Well, N dotted with V at 1 is equal to the magnitude of V, the speed, times the magnitude of N, 1, and the cosine of the angle between them, which is 180. So I'm going to go through this in every detail here so there is no confusion. So I've got P1A1 times the magnitude of N, which is 1, the magnitude of V1, which is V1, not a vector anymore, just a scalar, times cosine of the angle between them, which is 180. And of course the cosine of 180 is minus 1, so you see where this is going. So I've got minus P1A1 times V1 times minus 1, which is equal to plus P1A1 V1. Okay, so this is the flow work going in to the control volume at surface 1. Okay, at surface 2 now, so 2 is my outlet. Okay, I'm going to do this over here, maybe at 2. What do I have? I've got the work that is now out due to flow, right? Because flow is coming out of my control volume. It's pushing on the fluid that's outside the control volume. So I'm extracting work energy out of the control volume. It requires energy from the control volume to perform this work. So it's flow work out. That flow work out is equal to the force exerted by the control volume on its surrounding times the velocity at which it's going, which itself is equal to P2A2 times minus the normal vector at 2. That's the force exerted by the control volume on the surrounding fluid, dotted with the vector at 2. Okay. Well, in a similar manner to what we did before, that's equal to minus P2A2 times N2 dot V2. Well, in this case, though, V and N are oriented together because they're both pointing outside, so the cosine of the angle between them is going to be plus 1. So this whole thing here is going to be equal to minus P2 A2 V2. V2 is the speed at 2. Okay? Alright, so I've got an expression now for the flow work out. Oops, that should be flow right there. Flow work out, which is at surface 2, and the flow work in, which is at surface 1. So therefore, the work net in, sorry, let me call it flow net in is going to be equal to work in flow minus work out flow, which is going to be equal to P1A1 V1 minus okay, little error here. I'm going to have to correct that. Sorry about that. Right. So the force, the work is the force times the velocity, but they both have to be aligned. It's the force times the velocity in the same direction. So my vector right here is not pointing in the correct direction. That's the force exerted by the surrounding onto the control volume. But what I'm interested in here is the force exerted by the control volume on the surrounding, because that's the work that I'm extracting from the control volume. So really what I've got is a vector pointing in this direction that represents the force at 2, the force that the control volume is exerting on its surrounding, and so therefore the magnitude of that force is PA, a scalar, times plus N, a vector that points in the other direction. So let's correct what we've got over here. So that means I've got I've got F2 dot V2, so F2 is P2A2 times plus N2 dotted with V2, which is equal to P2A2 N2 dot V2. N2 and V2 are aligned together, so that gives me the net flow work out of the control volume, or the flow work due to the control volume exerting a force on the surrounding equal to P2A2 V2. Okay? Alright. Now the net flow work, therefore, is the work done, the flow work done by the fluid going into the control volume minus the flow work done by the control volume on its surrounding. So I've got P1 A1 V1 positive for the inlet flow work minus the outlet flow work, which is positive P2 A2 V2. Okay, that's the result I was looking for. And what I'm going to do next is, and that's the critical step, is manipulate this a little bit. I'm going to divide and multiply by rho in both sides. So I've just divided by rho here. Let's multiply by rho again. A1 V1 minus P2 over rho 2 of rho 2 A2 V2. So I haven't changed anything here, but you notice what I did is I've introduced this nice little m dot in both cases, at 2 and at 1. Okay, and that gives me my final result, what I was really after, which is the net flow work in, which is equal to P1 over rho 1 times m dot 1 minus P2 over rho 2 times m dot 2. And what I'm going to do with that is I'm going to substitute that back in that equation that I had for one before. So substitute in energy equation 1. Oops. And get, one moment. Okay, so what we're getting is the expression that we had for equation 1, which is everything that you get over here ending at the net work in to the system. And what I've done over here, oops, there's a little plus missing right there. What I've done over here is I've split the work in into two parts, the shaft work in and the flow work in. And we've got this result that we've just derived for the net flow work in. And when we substitute that in there, this is what we get. So we get the net heat in plus the net shaft work in plus P1 over rho 1 m dot in minus P2 over rho 2 m dot out. And then what we do next is we grab these two guys and move them to the other side. Oops. To give us our next energy equation 2, because P1 over rho 1 go in with the stored energy at 1 at the inlet, and P2 over rho 2 go in with the stored energy at the outlet. And all that we're left on the right hand side is the shaft work in and the net heat in. Okay, that's another form of the energy equation that is also very useful, very practical. And that's it for Reynolds transport theorem number 1 for energy equation. As promised, I've got the forms for multiple inlets, multiple outlets. That's our RTT number 2, given that the flow is still uniform and that the velocities are normal to the area. As usual, dead easy. Just slap a summation term in front of the two flux term. Flux of energy in is negative. The flux of energy out is positive. That's equal to the net heat in plus the net work in, net shaft work in. And finally, the Reynolds transport theorem in its whole general form. The only thing that's different from RTT number 2 is this flux term, which is now integrated over the entire surface and takes into account the fact that the properties may not be uniform at any given point over the area, so therefore we need to deal with infinitesimal regions of the control surface area, and it's equal to the same right hand side. That's it, just under 30 minutes. I hope you enjoyed the presentation. See you in class.